Hey everyone, hey everybody. Thanks for coming to our special April 1st edition of Papers We Love. Today we have Max Veytsman talking about Super Mario Brothers. There's a paper in there somewhere.
Hey. Hey everybody. Thank you for the introduction, David. The paper I'm going to be talking about is called, sorry, can you hear me okay? Is this like, good? Perfect. The paper is called The First Level of Super Mario Brothers is Easy with Lexicographic Orderings and Time Travel, ... After that, it gets a little tricky. By Tom Murphy VII Ph.D. Dr. Tom Murphy VII Ph.D. This is Dr. Tom 7. That's what he looks like. This is what I look like. I'm Max. I do stuff. I suddenly found myself working on a startup. I don't know. It's fun. So my slides say to start at the beginning. And my grade 12 English teacher, Miss O'Brien, told me that the foundation of Western literature was the Odyssey. So this is Polyphemus, who was a giant cyclops who trapped Odysseus in a cave in Sicily. He ate a couple of Odysseus' ship members, and there was really no way out. So eventually, while he was sleeping, Odysseus poked his eye out with a stick. But before doing so, he made sure to tell Polyphemus that his name was Nobody. And thus he established the two foundational principles of Western thought, which is create a fictional alter ego to take the blame, and puns. So you can see this in literature, where Cervantes claimed that the second book of Don Quixote was written by Sidi Hameti Benengali. You can see this in mathematics. This is a photo of the 1938 Congress of Nicolas Bourbaki, who was a collective pseudonym used by French mathematicians to establish the foundations of mathematics and set theory. And you can see this in computer science with Bovik. That is Harry Q. Bovik, a fictional computer scientist from Carnegie Mellon University, who's responsible for such papers as Counseling Artificially Intelligent Programs, which appeared in the Journals of Personality and Social Psychology, and Breath First Techniques for the Game of Life, which appeared in Artificial Intelligence Health. I went on that aside because this paper appeared in SIG Bovik, which is the special interest group in Harry Q. Bovik, which is held in CMU every year on April 1st. Today, in their proceedings, they include talks about artisanal type theory, beyond the halting problem, higher order infinite loop checkers, and bashing Haskell, re-implementing the parsec library inside the Unix shell. So SIG Bovik is a April Fool's joke conference, but this paper is entirely real. The software exists. You can even try to compile it, and this actually happened. So let's get started. This is a NES, Nintendo Entertainment System. Some of us had these. Some of us had friends that jealously guarded theirs. So it's an 8-bit computer. It runs at 1.79 megahertz, and it goes at something very close to 60 frames per second. And it has 248 bytes of RAM. So I wanted to build a comparison for this, so I went to the meetup page of this meetup, and the HTML without any images or JavaScript is 25.3 kilobytes compressed, which is more than 10 times this. And my computer has 8 million times this RAM, which means that on the NES scale, I can do big data easily. Yep. So the way that this paper plays NES is pretty straightforward. We're going to save the RAM of all the states for every frame as we play the game. We're going to find something in the memory that's increasing, whatever that means. And then we're going to play the game by choosing inputs that increase the bytes. So the first question to ask is, what does increasing mean? So obviously, if you have a score that's like a byte, it might go up. Your score used to be 0, now it's 1. It's bigger. But for lots of things, they're going to have a value higher than 256. So they're going to be in 2 adjacent bytes of memory. So Mario's score is going to be like 0, 1, 2, 3, 4, 5, 255, and then that byte is going to be 0, the next byte over is going to be 1. So we need to have a way of defining some kind of function that that can choose several bytes and increase with them even though one of them is not always increasing. So there's a really obvious and simple solution for this called lexicographic ordering, which is like how you sort a dictionary, right? AD is bigger than AA, but ZA is bigger than AD, even though D is bigger than A, Z is in the first position, so it comes after. So this is pretty straightforward. Then it gets a little bit trickier. So this is the part, I'm using this great PowerPoint clone called Dexet, which is awesome, except they charge you an extra $12 for an in-app purchase if you want formulas in LaTeX. And I was like, so I might have to use the whiteboard. So what we're going to do is we want to pick some sequence of bytes in memory. And we want that to present a lexicographic ordering on our memory. And this is the part where if you don't get it, raise your hand, stop me, and I'll try to explain it better. What I'm representing here at the top is we have the memory, we have 3 bytes, and at T1 it's 003, at T2 it's 002, at T3 it's 125. So we have 3 memory states increasing time. So we can just say our ordering is the empty set. And that is a perfectly valid ordering. Good job. Not very useful. We can say that the first byte, if we just take that first byte, that gives us a valid ordering on these memories. Because in the first memory, the first byte of T1 is 0, the first byte of T2 is 0, the first byte of T3 is 1, and that is a valid order. It goes from 0 to 0 to 1, which is always increasing, so we're good. We can even pick the first 2 bytes, because then we have 0, 0, 0, 0, and in the third one, the first 2 bytes are 1, 2, so we're always increasing. So we're doing a good job. But if we try to say, what if all 3 bytes give us a valid ordering, it doesn't really work as well anymore. Because we go 0, 0, 003 to 002 to 125, and suddenly we went from 3 to 2, and thus broke that ordering. Does that make sense?
Yep.
Most people? Okay. So 0, 1 is this a maximal ordering. What that means is I picked a sequence of bytes and I picked them somehow arbitrarily, but after I pick that set, I can't find any other byte that I can add to this ordering in the lowest significant place, and it still always go up. So that's the first part that we need. And why do we need this? We want to have these functions on our memory that have as much of the memory as they can. Unfortunately, if you look at the RAM of your Nintendo while you're playing a video game, there's a bunch of stuff that never changes. There's going to be a bunch of constants in play. There's going to be just junk that isn't related to your score that you're not trying to find. And that stuff is going to remain constant. So you want your orderings to be defined in such a way where they're maximal, but they're also tight, which means that every single byte that you care about at some point matters. So in this case, the second byte doesn't really affect our order, because when it changes, so does the first byte, which is in the first position. So it could not be there, and the order would still be the same. So what we want to do is we want to find an ordering which is both maximal and tight, a maximally tight lexicographical ordering. And we're going to find a bunch of these. We kind of do them with a sort of greedy algorithm where we just randomly pick a byte, then we search around for stuff that we can add, we pick one of them, and we build a bunch of these sets. It's pretty easy. So when we have that, we did this bit, we can go forward and we're gonna just record us playing a video game. And we wanna slice it up because If you don't, Mario's moving to the right, and that's great. You found a great objective function. You always want to move to the right, but sometimes you want to move to the left. So if you just record this function over the entire gameplay, it's not really going to work. So you need to find this little slice of time, and you say in which you define these objective functions. So you can sort of do it in contiguous blocks of time. What Tom 7 ended up doing is it's some mix of 400 frame sequences, and then taking values every 5,000th, 500th, or 5,000th frame, and it's pretty arbitrary. But you kind of split the memories that you have saved into slices, and you find these orderings on them. Then you weigh them. This weighing also happens in a very arbitrary way. There's a part in his description of this where he says, the mean value theorem or something is probably relevant here. Which it might be, we're not sure. But basically, you kind of say, oh, I have this function that goes across the memory. I want to see how do I say this? So each function is gonna have some range across the entire your entire recording of memories, and for every point you find for every memory, so every frame that you saved, you find where in that range it is. The idea is that you want your ideal function is gonna always increase, and so what he ended up doing is looking at the difference between its weirdly normalized value at the end and its weirdly normalized value at the beginning. It was weird. But without that weird weighing function, that's learn fun. And behind that is a graph of every single function that he defined over his entire gameplay, and they're all mostly increasing most of the time, except for the ones that weirdly jump up. But, it was good work. So you have these things, and now you can just kind of play Mario, which is play fun, the second half of this paper that plays Mario. So what are you going to do? You have a bunch of objective functions. You've weighed them all, so you have one, so you can now compute the value of any particular move. You can just press all the buttons, see what happens. Unfortunately, there are 8 buttons, so every single time you make that choice, you have 256 choices. And if you think about it, you're not just randomly, even if you think you're playing Street Fighter 2 and you're button matching, you're really not, because you're holding buttons for more than one frame, and you're probably pressing right a few times in a row. You're not actually randomly pressing buttons at each time that you can. So there's this thing called motifs, where you just, you have this recording of yourself playing the game, you've saved the RAM at every frame. So why not just take 10 button press chunks, save them as a library, and instead of choosing one button press, you choose the sequence of 10 button presses to play. So let's see how that works. So, oh, I can't see it here. So that's basically what happens. Mario does that forever. Because your score doesn't really change none of your objective functions, assuming that they're related to your score or something good happening in the game, they're not really going to change after one move. You have to look into the future a bit further than am I doing better now? It's oh, my height is bigger, so probably something good happened, and I'm somewhere in my objective function is height, so I'm just going to optimize for that and go like this. Yeah, it's too greedy. So, better way to do it is decide based on what he calls random futures. So a random future is, we're going to take 500 frames and just play randomly. We have these button sequences, we're going to just randomly jab at them, and then every time that we make a decision, based on that decision, we play out 500 frames of just random button presses, and we see which decision gives us this better randomly generated future. The idea here is that say you're falling down a pit, you don't know that you're going to die, but no matter what you do, in 500 frames you will be dead. So you know, you can now look in the future, and when you're on that ledge, you know that if you go right, no matter what you did afterwards, you're going to die. So that's a bad random future. and then ostensibly good random futures will come out equally. So the way that he tried to do this is he computes these random futures. You try to minimize, it's not quite like classical minimax, but you try to minimize the bad ones and maximize the good ones, and this is what it looks like. So there's Mario, and he's jumping around, but he figured out he can go right, even though he's kind of backwards. He can even like get over pipes, but not all pipes, because he's probably going to be stuck here. And he is. What happened there is that the screen kept moving. You saw like there's that bug where if you're next to a pipe, even though you're not going anywhere, the screen keeps moving, and that's awesome. Like some numbers going up, so that's great. So not exactly what we want. The other thing is that while playing, Mario never like really figured out how to move right correctly. He's always just like facing backwards and sort of jumping. So what we need is some way to learn how to play the game. I mean, we can't violate the aesthetic of this entire paper and actually program an AI that knows anything about how to play the video game that we're playing. So we need to do it in a more aesthetically pleasing way. So instead of, like before we just randomly generated some moves and started playing them, instead we're going to store about 40 sequences of moves. And at first you randomly generate them. Then every time you make a decision, you evaluate it just like you did before. You like play out these random moves, see what happens. But you also reevaluate all the moves that you stored. So if you find that, oh, this was a good decision, but like half of my moves are pretty shitty and I ended up not doing well, you throw them out and you replace them with another like sequence of random button presses. The idea is that eventually over time, not only are you winning the game, but there's this library of 40 sequences that you have is like turning into things that are reasonable to play in the game that you're playing, like maybe jumping right and running and not doing crazy stuff. So I think we can see how that works. And it's actually pretty good. There he goes. So now he jumped this one, jumped that one. And he gets stuck here a bit, but eventually he's going to throw out some of the stored random moves, and he's going to get an awesome jump. There he goes. And yeah, I mean, he's not the best Mario player, but he's succeeding. And I think he might even win this level. Nope. Maybe not. I guess not. You have to believe me, or you have to believe Tom 7. I actually have no idea, but that particular iteration can, maybe in the second or third try, beat the first level of Super Mario Brothers. The problem happens in World 2. So you're in this like dark reverse pit of despair, and he's doing pretty well, and he even knows how to do this, which is kind of tricky, right? Like getting under that ledge, you can't have a bad guy there. But then that happens. So Mario likes coins. Mario likes jumping up because it makes some numbers, some bytes go up. Mario also likes hitting that block up there. I think that like gave you points, right? Or something at some point. But he's not gonna like realize that you need to go back and keep going. So, in order to fix this, this is, of all the complicated, weird stuff that PlayFun does, this is the most complicated and weird. He added something called backtracking. So backtracking is, you're saving all these RAMs of your emulator, why not just like go back to one in the past and replay again? So the way that backtracking works is, in order to get out of local maximum, you checkpoint some state that you were at, you keep playing, and periodically you check like, hey, suppose that I went back like 1,000 frames ago and I did something different, would I be better now than I am? First of all, I mean, you can obviously try this a lot, but you have to know what does it mean to do something different. So in his case, it's just like a bunch of heuristics. You have your sequence of inputs that you got to go from the state that you saved to the state that you're at now, and you just like replace them with random moves. Or maybe you do opposite day, and like when you went left, you go right. Maybe you just like delete random pieces of the moves that you had, or replace them with just waiting. And then the only time you see integrals in this paper is right here. You got some integrals, and this is how you evaluate this is how you score your backtracking. So you basically compute the integral of your objective functions over your old path and over your new path, and then you compute the difference. You can't do an integral because you don't have a path. So he didn't really define, but he pretended to define a difference function between the objective function at your new end and your old end, and then you can compute a score, and then you can decide based on the score whether you should have gone back in the first place or not. That is a lot of it. There's a bunch of implementation details, which I kind of don't want to go into because I didn't find them particularly interesting. There was cool stuff that he did, like a lot of caching, and there was all these RAMs didn't compress very well, so he picked like basis memory states that he subtracted from every piece of RAM before compressing them, so you get a bunch of zeros. And then this thing was really slow, but the emulator that he was using was single-threaded, so he built MarioNet, which is networked Mario emulation, in order to like run the same thing over many processes, and he had his own little like orchestration bit that would send off jobs of emulation to different processes and get the result back. It's cool. I don't really want to go into describing those things. What I want to talk about is the immersion behavior. So Mario would like lovelily exploit bugs. For instance, here's Mario, and you ever seen that move? That was an awesome move. I think he does it in slow motion there. Oh yeah, he punched up. And the way that you kill a Goomba from the bottom, I am not enough of a Mario fan to know this, maybe some of you are. Apparently when you're going up, if you press the down key at the right moment, then Mario thinks that you're falling on the Goomba, even though you're getting them from the bottom, so you become invincible. So yeah, you can, like, if you have really good timing or a computer, you can kill Goombas like that. The other thing that this AI does is realize that sometimes the only winning move is not to play. So this is the same AI, just trained on Tetris. And it sucks at Tetris. It is really bad at Tetris. But it knows that you can do that. And you never lose. And that's it. No other move. Yeah.
Was that Mario bug? Was it a known bug that you could do that?
I don't know. I've never heard of it. Have any of you heard of it? Yeah.
I used to use it. It depends on you hitting the Goomba from a specific angle too. If you hit it from directly below, you die. But if you like diagonally hit it, it's good.
Can you do it without having an emulator? Like, can you do it on an actual Nintendo?
Yeah, you can do it on NES.
Okay.
It's been a while, but I remember being able
But like humans can do it. It
Yeah.
doesn't require super precise typing. Yeah, apparently. So that's actually it. All I have left is group discussion about the aesthetics. Yes?
You know, in the backtrack, you know when he was caught, he started backtracking because he was going up and down, up and down.
Yeah.
And is there a timer involved there? Did he put a timer in? So you only backtrack after a certain amount of moves, or you don't need a timer? You know, or a number of moves, like 1,000 moves that do, like repeating this.
You backtrack every, like there's a constant for how often you try backtracking, and there's a constant for how far back you go. Because it's really stupid to like go back to the beginning of the game and play the whole thing over. So you're only going within a set window of where you are, and you do it every so often. And in the paper, he has these like arbitrary constant warning, and it's just like random numbers that he kind of chose. The other thing I forgot to mention about the backtracking is that it actually didn't solve that ledge problem. What solved the ledge problem was the fact that, according to him, while writing this paper, he realized that there was a bug in that really complicated weighing function that was stopping, like, that actually was what stopped Mario from being able to go over that ledge. And when he fixed the bug, even though he had backtracking, it actually started working then. That's it for me. If you guys want, we can watch a video of Mario picking stocks, or of this AI picking stocks. People are. Can I do this with sound?
Yeah, it'll have to come through that.
It's muted, it's muted.
How do I unmute? How do I unmute?
Game called Wall Street Kid.
Okay. Let's try this again. This is like my favorite. You should watch the videos. This is my favorite sequence.
Remember, this is
You
mid
hear it?
80s, so
You got plenty of
it's gonna be really douchey. And basically, this is the intro. This lawyer is telling you that you just inherit a bunch of money. If you can double your $500,000 in 1 month, then you get the whole inheritance, and which is ridiculous, of course. But people wanted to see how PlayFun did on the stock market, so this is how it does. And here you have, using our lesson from before, see, it says, "Have a great April Fool's Day, but remember, everything I told you is no April Fool's joke." Just like this software. By the way, this is
So for some context, way better than in the paper. He like really instrumented the graphics really well. So this is the entire RAM of the Nintendo, and the colors represent how good the AI thinks that bit of RAM is. That is like pretty much the same graph, but like in the past. So it's giving you an aggregate of how good or bad it thinks it's doing over time. And these are each individual objective function graphed over time. So with that being said, this is this thing playing Wall Street.
basically you read the hot stocks bulletin, headliners, and so forth. Get some phone calls from your agent. It's like there's nothing fun in this game at all. So in this game you control that little arrow which you can drive around and click on flowers or whatever. We get off to an auspicious start. Immediately goes to buy, which is what you have to do in order to just buy 6,000 lots, each 100 shares of AT&T. No? Okay, how about 4,002? It's telling you right here, 8 max. So we're off by a couple thousand. And he spends some time on this screen trying to buy way too many stocks and fails to do that. And then watch these expert cursor skills. This is what I imagine like life and finance is like. Just trying to decide, should I read the paper or should I touch the computer?
stock picking with this AI. So if any of you are into financial engineering, look somewhere else. I think that's it for me. Any questions?
So are the objective functions like a function of every piece of RAM to some input, or is it like, or sorry, the objective functions are like functions that tell it how good it's doing?
Yeah, so you pick a bunch of, but you pick some subset of the RAM in some order, and that is that little objective function. So it's like some subset in some order, and then you apply it at every given frame to the entire RAM, but it's only looking at that subset. And then you just like the weighted sum of that is kind of what you're trying to maximize or minimize.
So that's what, okay, so then it's the other functions that you were talking about, like, that look at random futures and stuff like that, that actually decide the inputs?
Yeah, so the way he splits it off is learn fun and play fun. So the learning part is you build a library of those, and I think you also give them the weighting. And then the play fun part is you're taking that data that you gathered and you're making like decisions per frame based on the output of those functions.
Going back to learn fun for a sec, you showed an example of making a lexicographic ordering from a series of bytes.
Yep.
And that was like one ordering, right? Do you know if learn fun had like many different orderings, or were all of the potential bytes to consider put into one lexicographic ordering?
No, so each color on this graph is a different ordering. It's a different subset, and it's a different ordering. So you could potentially have one that's just one individual byte. The fact that they're maximal means they all probably have some pretty large set of bytes in them. But there's a hard-coded constant, I believe, of like how many you try to get.
Did you try play fun?
I have not. I tried to get a VM and to compile this, and I couldn't. And then I had to make these slides. So I was like, I will probably just make these slides. Have you?
No, I haven't. I was wondering how hard it would be to compile.
I think it's not easy.
Yeah.
It is in C++, and it is like a hacked version. It's a hack on a hack on a hack. So have fun. All right, I think that's it. Thanks, everyone.